So apart from peak and valley voltage, two other parameters are going to specify the behavior of the diode. So one is peak current. The peak current we have seen, the peak current is 2 milliamperes. The peak current is 2 milliamperes. And next one, the ratio, the peak to valley current ratio. The peak to valley current ratio is what is the ratio between peak current and valley current. Peak current is 2 milliamperes, valley current is 0.2 milliamperes. Divide both, so 2 by 0.2 is going to be 10. So the peak current is 10 times larger than the valley current. So it is 2 milliamps and 10. So these parameters, peak voltage, valley voltage, peak current, and peak to valley current ratio will determine the behavior of your tunnel diode. Okay, so the VI characteristics are already shown. We have seen the VI characteristics. Now the energy diagram energy band diagram is shown here. So you can see the energy band diagram, and no voltage, no bias is obtained in the conduction band and a valence band or in same energy level. So as I'm going to increase the positive voltage, the electrons will flow easily because the depletion region is very thin. And the P side energy band is also less. But as you, this happens at peak voltage. But as you keep on increasing the voltage, the energy level in the P side increases, which will restrict the flow of electrons into the device. So that is why the current is reducing. So energy level, the energy structure will, and the energy bands will vary with the applied voltage. So when initially when you're increasing from 0 till the peak voltage is obtained, that variation in energy band level is very, very minimum. So electrons will start flowing from N type into the P type, contributing to current. When you are going to increase the voltage beyond the peak point, the energy band will rise on both sides in N and P region, which makes it difficult for electrons to cross the depletion barrier. So it is not like the current is completely zero. No, some charge carriers will cross the potential barrier and reach the other side, contributing to current. But what we see is that current is very, very minimum. So the level to which electron energy states are occupied by electrons are shown in either side. When the bias is zero, there is same, the energy bands are at the same height. So you don't expect any current flow. Unless energy is imported to electrons from external source, the current is not going to flow. So when I'm going to slowly increase the voltage, this energy is possessed by electrons and they climb over the potential barrier to reach the P side. However, we have seen that there is a probability for tunneling. So there is a property called tunneling in PN junction diode. Instead of drifting, they use tunneling to cross the depletion region. Okay, so that is what is done here. So when small forward bias is applied, the energy level of P side will become less, contributing to what is the current. So the tunneling of electrons will take place from N side to P side. So tunneling in other directions is not possible because the valence band is now on the opposite side of the N side. So the electrons will not tunnel back because one side the energy is high, one side the energy is low. So electrons will never go from lower state to higher state unless you apply energy. So they will always go from upper energy level to lower energy level. So that is going to be the forward bias characteristics of your tunnel diode. Okay, when the forward bias is increased beyond a particular point, the tunneling will decrease. So when majority of the electrons have crossed the depletion range, tunneling will slowly start to reduce. So the energy on the P side is depressed further, so which will result in fewer conduction band electrons in the opposite to the P side energy levels. So it all depends on how much vacant energy levels are there in the other side. So that will determine how much electrons are going to move from N side to P side. So initially, when the forward bias is applied, there are a lot of vacant states, so more amount of electrons will tunnel to the depletion region and reach the P side. Now in P side, the vacant states are less. So when the vacant states are less in P side, even though you increase the voltage, the number of electrons crossing the barrier to reach the vacant state is also less. Okay, so that is the reason why they say the forward current is going to drop. The forward current is going to reduce. So this corresponds to the negative resistance region. I again say negative resistance region is interpreted by usually as you increase voltage, current will increase. I will increase. Okay, but in negative resistance, instead of increasing, the current will decrease. So instead of increasing, the current will decrease in negative resistance region. So after that, when the forward bias is going to increase further, the depletion region width will also grow, and it become the size of your width of the PN junction diode. So it will work as a conventional PN junction diode. So this tunneling phenomenon happens only when the depletion region width is very, very small. When you're increasing the voltage, two things: the depletion region width is also slowly increasing, and the vacant states are also completely occupied. So this prevents further tunneling of the charge carriers from the N side to the P side. So this is the equivalent circuit of tunnel diode. So tunnel diode, you see, you will have a series resistance RS, you have a inductor LS. See, all these components will come whenever you are going to have a semiconductor device. You are going to have two wires pulling out. So for that, you will have a resistance, and whenever current is going to flow, you will have an inductive magnetic effect that is quantified as inductance. And this you have a depletion region width is constantly varying, so you have a capacitance effect, and you have a negative resistance, so you put a minus Rn. Okay, negative resistance is modeled as minus Rn. So the typical values are given here: Rs equal to 6 ohms, Ls equal to 0.1 nanohenry, Cj equal to 0.6 picofarad, and Rn equal to 75 ohms. So these are the typical characteristics of our tunnel diode. Symbol for tunnel diode, you see, in the normal diode symbol, we put a T. This T is going to say it is going to be tunnel diode. So this is the symbol for tunnel diode. You can encircle this one to get the use it in our normal diodes. So normal diode, you put for normal diodes, you put a triangle and a line. When you extend the line to form a T on both sides, it becomes a tunnel diode. That's all. Remember it like that. Okay. Application is very, very simple. It is used in high frequency switching applications where the depletion region is very, very small, so the charge carriers can cross quickly, right? So it can turn on and turn off very quickly. So that is the first point. You see, it is used in ultra high speed switching circuits as a logic memory storage device. It is a microwave oscillator. See, remember, any device having negative resistance region will oscillate. That means that region is unstable. Any unstable thing is going to oscillate, right? So this is used as a microwave oscillator. It is also used in relaxation oscillator as well as in amplifier. Advantages: it is having a low noise and easy operation, high speed, and it consumes only low power. Drawbacks: it should be operated within less than 1 volt. So low voltage operation only is preferred for this diode because the depletion region is very, very thin, right? So even at a very small voltage, enormous amount of current is going to flow. So this diode is preferably used for low voltage operation, and it is a two-terminal device, and there is no isolation. Isolation means input and output side are separating input and output side. Here the depletion region is very, very thin, so that is not going to separate your input and output. So if the input is going to catch any noise, it will be directly passed on to your output. So that is the drawback in this tunnel diode. Just because we want to make our depletion region smaller and smaller, we are going to make all these. We have to get all these disadvantages.